So, hello everyone. I will present to you our work towards a combined method for the optimum management of building demand and supply thermal loads. First, I will talk a bit about the current state of the art on the energy management in buildings. When we focus on the supply side energy management, we can see that the energy producer objectives mostly concern the minimization of the operational cost and the satisfaction of thermal demands of the consumers. At the same time, energy producers manage thermal load provided to consumers through thermal power reduction and energy tariff variability. On the other hand, when we focus on the demand side energy management, we can see that thermal consumer wants to optimize the energy cost, minimize the energy cost, and maximize their thermal comfort. However, thermal comfort is considered only a constraint and not an optimization objective at the moment, and that makes the optimization procedures limited to a single objective. So what we propose is an algorithm that will allow the users to make some trade-offs between thermal comfort and energy cost using a multi-objective optimization approach. So our methodology basically, we create a simulation environment of a building and a thermal system where we apply the optimization criteria of the users, which are the minimization of the energy consumption cost and the minimization of thermal discomfort, which is otherwise called maximization of thermal comfort. So through the simulation of some scenarios and the application of the proposed algorithm, we are able to form a Pareto front, which is a set of equally optimal solutions. And through this Pareto front, we can create a heating frequency of intervals, which will allow us to evaluate the multi-objective optimization algorithm in terms of adaptability on optimization according to different strategies and possible uses in real cases. So the purpose here is to create essentially an algorithm and use three scenarios which are the conventional heating operation, the second one is the forced heat load reduction, and the third one, which is most currently used in the electric sector, recent one, the economic incentives. So here we have the simulation environment along with the heat system model and the building model, which is an end-user model built on the Python environment. The scenarios that were examined, as I said before, are the base scenario, which is during which the thermal system uses the 100% of its load power while we keep a constant energy tariff throughout the simulation period. In the second scenario, we'll use the thermal capabilities of the thermal system, but we maintain the constant energy tariffs, while in the third scenario, we are using the full power of the thermal system, but we have variable energy tariffs. So to move to scenario one, in detail, we can see that we are implementing a 2-day simulation where we are trying to build our way to max comfort target, which is 100%, where the occupant feels comfortable. The simulation time step is 1 minute. And the office concerns mainly an office building. So the occupancy period is a typical 8 to 5 working period, and the temperature set point is set at 20 degrees of Celsius. Here, as I said, the thermal power is set at full power at 3 kilowatts, while the energy tariffs are kept at 12 cents per kilowatt hour thermal. So when we apply the algorithm, we can see we can create the Pareto front, which is on the left graph. And we can see that we can produce equally optimal solutions along with the comfort optimal solution which the conventional heating systems are implementing at the moment, which is the green dot, the green scenario. But we can also produce some alternative heating schedules, like a random one colored in orange. And we can see the differences between the green and the orange are that in the green one we strive to maximize thermal comfort, but on the orange one we decide to sacrifice a bit of comfort to reduce the cost. And when we move to the detailed view, we can see on the graphs the operation both of the building and the thermal systems. And we can see that the algorithm is able to find, to use preheating by itself in order to maximize comfort. However, in the green optimal case, of the optimal comfort scenario, the green one, while we wanted to achieve 100% thermal comfort, we only managed to get 91, which means that the algorithm was trapped in a local optima. So I will skip scenario 2 because it is not very useful at the moment, but it was more like something we tried to see how the algorithm will react to it. And we'll go to scenario 3 of the economic incentives, which differs from the first scenario on the fact that the energy tariffs are now variable. We can see that during the early morning hours and the late evening hours, the thermal energy cost is reduced, while on the morning and noon hours, the energy cost is increased. And by creating the Pareto front on the left graph, using thermal discomfort and consumption cost as optimization parameters, we can see that we are gaining, this time we managed to achieve 100% thermal comfort. This is mostly matter of the algorithm at the moment. And when we move to the detailed view, we can see that when we pick the comfort optimal scenario, which would be a conventional thermal system at the moment, and compare it to the respective of scenario 1, we can see that the algorithm has opted for heating the building earlier because of lower prices during the early morning days. And moreover, the algorithm has identified that heating during the first day is more valuable than that of the second day in terms of thermal comfort. We see that when we compare the green scenario to the green case, the comfort optimal, to the alternative case, because during the second day, we can see that in order to cut off some energy and save some money, the algorithm decided to turn off the heating at the late afternoon time of the second day. So when we put all the scenarios together, along with scenario 2, which I did not present, we can see that thermal discomfort is preferable as a criterion compared to thermal comfort. And this is because when the algorithm tries to form the Pareto frontier and expand its heating schedule, we can see that in many cases, on the right graph, thermal comfort is the same, while the energy consumption cost is different, which means that algorithm is likely to be trapped in the local optima during optimization, and therefore discomfort is a bit more is a bit better when used as an optimization criterion. Also, we can see that in scenario 2, the forced load reduction was so intense that 100% thermal comfort was physically unattainable, which means that we have to check how much we reduce the thermal capabilities of the building. And the algorithm cannot do anything about this, because no matter how much it preheats, thermal comfort will not be increased. So we saw that the algorithm works adequately well, and now we are going to form some preferred heating periods, in the meaning that we can see that when we take the Pareto frontier and examine each case and take the hours during which heating was on and put them all in a graph, we can see in how many cases did the heating turn on each time. So we can essentially get an estimation of which heating periods are more valuable. And as we can see on the scenario 1, for example, it is confirmed that day 1 is more valuable to heat than day 2, because when you heat during the first day, the second day the building will also be warmer, will have retained some of the thermal energy from the first day of heating, which is logical. We can also apply different strategies and create the heating frequency graph in order to see how different heating strategies can affect the optimization. And this is a great way to evaluate solutions and strategies on a one-dimensional scale while retaining the multi-objective nature, because we have not used any weights on which criterion do we prefer, thermal comfort or energy cost. So if we apply this logic to our two scenarios, scenario 1 and scenario 3, we can see that by reducing the energy cost during night hours, the algorithm manages to exploit this and create heating schedules that where heating costs less during night periods. So we have managed to shift the heating loads towards early hours in each day, and that will certainly lead to a big saving of energy. So the algorithm works as intended, but what can we do with it? The benefits of the proposed algorithm. The benefits of the proposed algorithm is that it provides a Pareto front, while the conventional heating devices at the moment provide only one solution, which is fully attain 100% thermal comfort, while keeping the energy cost as low as possible. While here we have the whole Pareto frontier, so instead of picking the green solution, which is the conventional, the user might want to pick some solution that is close to the green one, but will enable him to save a lot of money without sacrificing a lot of comfort. And finally, the proposed methodology and the optimization algorithm could provide a useful tool for energy management on a multi-objective scale, since in that case the energy producers can declare the heat conditions that are going to be implemented in the form of how much heating energy is provided to the consumers, or how much does the energy cost. The users can provide the preferred heating periods according to the produced results from the Pareto frontier, and therefore the producers can adjust and reevaluate the heat conditions that are going to be implemented. So this was it. Thank you for your attention.